The purpose of this video is to talk about the meaning of curvature, specifically curvature of plane curves where the curve is parametrized, and then derive a user-friendly formula which can be used to calculate the curvature of basically any smooth parametrized curve. In a nutshell, curvature measures how much the curve bends or changes direction, I guess you could say, at a point. When I talk about changing direction, I'm talking about a change in direction of the tangent vector. And the direction can be measured in terms of the angle between the tangent vector and any fixed angle in the plane. For lack of a better one, we might as well use the unit vector I. So let me put that in here. So I points in this direction. And the angle between B and I is this angle here. And of course, as this point moves along the curve, let's say that we're moving in this direction here. The curve, let's say, is oriented that way. As the point moves, the velocity vector changes direction, but of course I does not. So that's where theta is sort of varying. It's varying as the point moves along the curve. In this case, if you were moved to the right, it looks like the angle between V and I would be decreasing. And that is in fact the case. So what we need to do is come up with a parameterization. Let's see, I'll just use black. Parameterization, general parameterization, of course. We don't have a specific curve here of the curve. So let's say R of t is just x coordinate function x of t, y coordinate function y of t. And of course, the way that we get the velocity is by taking the derivative of r and for brevity, I'm just going to write let me change those. I like to think of the position function as producing a point, and of course the velocity function produces a vector. It's a very subtle distinction, but I think it works. It certainly works for me. So the angle between V and the unit vector I is the same as, of course, the angle between V and the horizontal. So let me draw a picture sort of representing what's going on a little bit differently. Get this thing to draw. Okay, so here's V. Here's the horizontal. And I'm going to draw a couple of other vectors. I'm going to draw x prime and y prime specifically in this picture. So here's x prime, that's the horizontal component of velocity. And here's y prime. And notice that the tangent of theta is y prime over x prime, opposite over adjacent. And so theta is the arctangent of y prime over x prime. Now, if x prime happens to be 0, then that's a problem. However, nothing says that I can't use, instead of using I as my as the vector that determines the angle theta, or the angle theta that I'm using in the problem, I could use j, which of course points upward, in which case these would be switched. If x prime and y prime are both 0, then the curve is actually not smooth. Okay, so now let's take the derivative of, so we're looking for the rate of change in the direction of the tangent vector v. That's done in terms of the angle. So rate of change of angle is what we're looking for. So d theta dt. Okay, so first of all, we're taking the derivative of arctangent. The arctangent of y prime over x prime. So that's going to be 1 over 1 plus y prime over x prime squared. But then per the chain rule, we have to multiply by the derivative of the inside, which is going to require the quotient rule. The quotient rule says take the derivative of the top, which is y double prime, times the bottom, minus the top, times the derivative of the bottom, over the bottom squared. Okay, so we have some simplification to do. Let's create some more space. So this is 1 over 1 plus y prime squared over x prime squared times all this stuff. Whoops, it should be an x. And notice if I multiply the x prime squared by this denominator, I get, actually let's just multiply fractions in the usual way, multiply the numerators. So y double prime times x prime minus y prime times x double prime. And as I was going to say, when I multiply this denominator by x prime squared, of course I have to distribute. When I do that, I get x prime squared plus y prime squared. One of the problems of this formula is that it does in part measure the rate of change of the velocity vector, the rate of change in the direction of the velocity vector, but it also is influenced by the speed of or the velocity of the particle as it moves along the curve. An interesting fact: if you double the velocity, that actually quadruples the acceleration. By the way, the acceleration is, or the components of acceleration are embedded in this problem here and here, just so you know. And we need to eradicate the effect that the speed or the velocity, the actual speed, has on this measurement. So what we do is we just divide d theta dt by speed. Now remember, the speed is the norm of the velocity, which is the square root of x prime squared plus y prime squared. If I divide this by this, let's create some more space. Whoa! Then I get following. So what's going to happen is, as I said, when I divide this by this, in the denominator, I'm going to end up with x prime squared plus y prime squared to the 3/2. And this is the what we're defining the curvature at R of t, where R of t is just some specific, for a specific value of t, R of t is a specific point on the curve. So here's a formula. Now there are some things that I can do to modify this slightly to make it look, I guess, a little bit nicer. One of the things I can do is notice that the numerator is actually, oh, there's one other thing I should mention. This rate of change of the angle, I don't care whether the angle is decreasing or increasing. So when we make our definition of curvature, I should mention we're going to actually take the absolute value of all this. And when you take the absolute value of the denominator, it's not going to change. So really, we're talking about this. The absolute value stays on the numerator because we don't know if it's positive or negative. Okay, so now what I was going to say is this is actually the determinant of a matrix. This is actually the determinant of this matrix. You can see that if you multiply, if you calculate the determinant, it's x prime times y double prime, which is this, minus x double prime times y prime, which is this. Also, x squared plus x prime squared plus y prime squared to the 1/2 is actually the speed. And the speed is the norm of the velocity. So it's that cubed. And then notice that this, if you think of this first row as a vector, that's the velocity vector. And the second row is the acceleration vector. So this is absolute value of the determinant of first row b of t, second row a of t, divided by the norm of v of t cubed. And there's our formula for the curvature of a parametrized curve.